Hello class, welcome to this lesson on 5.2. We're going to be talking about properties of exponents and radicals. More specifically, we want to look at properties and radicals and use them to rewrite radical expressions. So we're going to be talking about like radicals as well as reduced radical form. Alright, so we're going to start with the properties of rational exponents. These are the same properties that you use for any kind of exponents. Regardless of whether they're whole number exponents or fractional exponents. So you may recall some of these. So for example, if you got the product of powers and you're multiplying two things, you usually end up adding the exponents as long as the base is the same. So for example, 4 to the 2/3 power times 4 to the negative 1/3 power. Notice that the base 4 is the same, and you're multiplying these two things together, so you're simply going to add the exponents. So in this case, we're going to do 4 to the 2/3 plus negative 1/3 power. Really, you're adding these two exponents together, but because this one is negative, you're really subtracting these two exponents. So it's really 2/3 minus 1/3. They have the same denominator, so you can go ahead and subtract the numerators, and you get 4 to the 1/3 power. So that's the product of powers property. The quotient of powers property is going to be when you divide with the same base. So if you're dividing with the same base, then you're going to subtract the exponents. So in the case of 3 to the 4th power divided by 3 to the 2nd power, you're going to keep the base the same and then subtract the exponents together. In this case, you get 4 minus 2, which is 3 to the 2nd power. Again, this works with fractional exponents as well. So for the next property is the power of a power property. So it's basically when you raise a power to another power. I also call this power to the people. When I talk about power of product, I call that power to the people, which is the next one right here. So power of product is basically an extension of power, in which you have multiple things inside that parentheses. So therefore, power to every single one of those, hence power to the people. Now for power of power, it's just a single thing inside, so you're just going to multiply the two exponents that are next to each other. So in this case, we got 7 to the 3rd power raised to the 2/3 power. So you're simply going to multiply those two exponents together. So you got 7 to the 3rd times 2/3 power. And then remember, you can multiply these two fractions together. So multiply straight across. If you put an over 1 for the 3, and then you get 3 times 2 is 6, and then 3 times 1 is 3. So you get 7 to the 6/3 power, but that's just really 7 squared. Alright, so remember that this is not the same thing as 7 to the 3rds times 7 to the 2/3. Those are not the same thing. Remember that in this case, with the 7 to the 2/3 power like this, right, this bottom one, you would add the exponents, right? So in this case, you would add the 3 plus 2/3 power together, whereas in this top case, you're multiplying. So these are two totally separate things. Okay, so the next one, like I mentioned earlier, is what I call power to the people. When you have multiple things inside the parentheses, you can distribute essentially that power throughout to everyone. So in this case, you have a 16 and an x inside the parentheses, so you can distribute the 1/2 power to both of them. Now when you distribute the power to both of them, it's important to realize that you're really multiplying the exponents. So for example, the 16 here is 16 to the 1 power. So if I distribute the 1/2 power to the 16, what I'm doing is I'm multiplying the exponent of 16 to the 1/2 power. So really, this is the same thing as 16 to the 1 raised to the 1/2 power, and then x to the 1 raised to the 1/2 power. The reason why I do this is to make you realize that you're multiplying these exponents, right? You're doing 1 times 1/2, and you're doing 1 times 1/2 here. So 1 times 1/2 is still going to be 1/2. So it's really 16 to the 1/2 and x to the 1/2. Again, this may sound silly to put the 1 power there, but imagine if you had something like 16 squared x to the 3rd and then raised to the 1/2. Well, then if you distribute this, well, then you have to basically multiply the exponents together, because you're going to do 2 times a half, and then you got to do 3 times a half, like that. So then in this case, well, it's not so trivial, right? So now you have to actually multiply them. So you get 2 times a half, which is 2 halves, or 1, and then 3 times a half is 3 over 2. Okay, so in this case, it's not so trivial, right? So the next property that we're going to be looking at is the negative exponent properties. So we kind of touched upon this in one of the examples in the previous lesson, but now we're formalizing it. This is the rule for the negative exponent. So really what you're doing, what I call, is the old flip and forget. So you're going to flip the number, so it's 1 over, and then you're going to forget the sign of the exponent, and therefore you get it, the exponent is positive. So in the case of 5 to the negative 1/2 power, you're going to flip it, so it's, instead of it being 5 over 1, it's 1 over 5, and then you're going to forget the sign, so it's going to be 1 over 5 to the 1/2 power. Alright, so keep in mind that we're not converting this to a radical, we're just using the property. Of course, if they want you to convert it into radical form, you would have to convert this to, the square root of 5, for example. Alright, so example 1, we want to rewrite using the properties of exponents as explained earlier. So for part A, we have a product. So basically we're doing a product of power here, right? So this means that if we have the same base, and we're multiplying, then we're going to add the 2 exponents together. So in this case, we're going to keep the base, which is going to be 81, and we're going to raise it to the 5 over 6, and then we're going to add it to 1 over 3rd power. Okay, so we got to do 5 over 6 plus 1 over 3. So what I'm going to do is I'm going to do that off to the side here. I know I got to add those 2 fractions together, so we might as well do that off to the side, just so that we can get that work out of the way. So we need a common denominator. Well, the common denominator here is 6. So since the common denominator is 6, this means that I need to multiply this by 2, and whatever I do on the bottom, I do on the top. So now I have 5 over 6 plus 2 over 6, which is going to be 7 over 6. So there's my fraction now. So now I can rewrite this as 81 raised to the 7 over 6 power. Now, of course, I can go and simplify this, but the point of this exercise is not to necessarily simplify, it's just to use the exponent properties. If I were to ask you to simplify this, then you're going to have to use the methods of the previous lesson, in which you would say, well, this is the same thing as 7 over 6 is the same thing as 1 and 1/6. And the way you get that is 6 goes into 7 once, and then you got a remainder of 1. And so you can write this as 81 to the 1 and 1/6 power. And then basically you can rewrite that as 81 to the 1st power times 81 to the 1/6 power. And then basically now you got 1 and 1/6. So you got basically 81 to the 1st power, which is just 81. And then you got 81 to the 1/6 power, which according to the previous lesson, power over index. So this is going to be a radical with a power of 1 and an index of 6. And that's how you would simplify that. That's one of the ways in which you can simplify that. But again, like I said, we're concerned with simplifying this. This answer would suffice for this example. So for part B, we're going to go ahead and use a couple of properties here. So we have a quotient of a power property. So we're dividing 2 things together with the same base. In this case, the x's have the same base, and the power for this x on top is 1. The power on the bottom is 1/2. So since we're dividing, we're going to go ahead and subtract those exponents according to that property. So I can rewrite this as, so I know that I have the x raised to the 1 minus 1/2 power. So I'm going to write it as x to the 1 minus 1/2 power. Now that y is on top along with that x. So that's y stays on top like that. Okay. Now remember, I only write the base x once, so therefore it's only written once. I'm not writing it twice. And then of course we got the 2/3 power there, so that we got to write down. So we got 1 minus 1/2. So 1 minus a half is 1/2. And then we got y to the 3rd power, and then this whole thing is raised to the 2/3 power. So now this is a combination. This is basically power to the people, or otherwise known as, the product of powers. If you look at that other property, so basically we're distributing the power over to both exponents. So we have here x to the 1/2 raised to the 2/3, and then you got y to the 3rd raised to the 2/3. So you're basically multiplying those powers together. So we got 1 times 2 is 2, 2 times 3 is 6, so we got 2 over 6, and then we got 3, so y has an invisible 1 down here. 3 times 2 is 6, 1 times 3 is 3, so this becomes y to the 6 over 3 power. And then 2 over 6 can be reduced to, you can divide it top and bottom by 2, in which case, in which case you get x to the 1/3 power, and then y to the 2nd power, 6 divided by 3 being 2. All right, and that's our final answer, without having to simplify or anything like that. Pause the video and try the following problems. All right, so we're going to rewrite using the properties of exponents, just like we did before. So we have here a quotient. We have 3 on the top, and then we have which should be a 32 on the bottom, raised to the 1/2 power. Okay, so what you're going to do is notice that we have a quotient here. We have so basically we have a bunch of stuff raised to the 1/2 power, right? So we're going to distribute the 1/2 power to everything. Now, right now, I can't divide the 3 and the 32. I can't do anything with that because we have different bases here. We got a base of 32 here. We got a base of 3 here. So basically, we can't do anything with the exponents for that. So the only thing we can do at this point is distribute that 1/2 power to everything inside, which means the numerator and denominator. So we have here 3 to the 1 times a half. 1 times a half is a half, so you're just basically making it 3 to the 1/2 power. And then this one you got to do 32 to the 2/5, and then you got to multiply by 1/2. So we got 3 to the 1/2 power divided by 32 to the 2/5 power times a half. So we got to multiply those two fractions together. So 2 times 1 is 2, 5 times 2 is 10. So we got 32 to the 2/10 power, which that reduces to 1/5. So we got 3 to the 1/2 over 32 to the 1/5 power. Again, we can't do anything with those exponents because the bases don't match. However, we can leave it like this, or we could write it with the 32 on top, where we have 3 to the 1/2 power times 32 to the negative 1/5 power. We can write the 32 on top as long as we have a negative exponent because of the simple fact that we flipped the 32 up. So if you flip it up, you're going to make the exponent negative. So either one of those would suffice for the correct answer. All right, now notice that we're not simplifying this at all. We're only using the properties, okay? So technically you can simplify the 32 to the negative 1/5 power, right? You can actually simplify that, but we're not concerned with that at this point for this problem. All right, so for part B, we have a few things going on. We have a power to the people on the inside here, where we're going to distribute the 2/3 to A and to the B here. And then we have a product of powers. Okay, so we're going to do the power to the people first and distribute that 2/3 first. Okay, So we have here 2a to the 1/3 power times, and now we have in the inside, well, we don't even have to put this in parentheses, but I will just to kind of show you. This is a to the 1 power raised to the 2/3, so I'm distributing the 2/3 to the a, times b to the 1/2 power times 2/3. So again, distributing that 2/3 to both of them. So 1 times 2/3 is just 2/3, so this will be 2a to the 1/3 power times a to the 2/3 power times b to the, now we got to multiply this. This is going to be 1 times 2 is 2, 2 times 3 is 3. So this right here is going to give us 2/6, but we're going to go ahead and reduce that, and that's going to give us 1/3. So we're going to put that over here, okay? So this is going to be to the 1/3 power. All right, so we saved ourselves a little room by doing that calculation off to the side. Now what we're going to do is we're going to use this part. We're going to do a product of a power. So since they have the same base, we can add the exponents for those two. So we have 2a to the 1/3 plus 2/3, like just like that, times b to the 1/3 power. You can't do anything with the a and the b because they have a different base. So therefore we're just going to add the exponents for a. So we got 1/3 plus 2/3 is 3/3. So this is going to be equal to 3/3, which is equal to 1. So we're going to just ignore the exponent for a. It's just an invisible 1. And then we have b to the 1/3 power. All right, hopefully you were able to use the exponent properties or kind of get a handle of which properties to use. Okay, so now that we talked about properties of exponents, we're going to briefly talk about properties of radicals. So there are a couple of properties that you need to be aware of. So the first property is the product property of radicals. The nth root of a product is equal to the product of the nth root of those numbers. So basically, if you have a radical and you have a product or a multiplication inside that radical, you can split that radical into two separate radicals multiplying each other. So we've already done this before, right? When we break apart a number such as the square root of 40, we can break this up as the square root of 2 times the square root of 20, for instance. So that's legal in the math operations, so we can actually do that. And then, or we can go backwards and just multiply it inside, right? 2 times 20. So this is one of the properties that we can use. That property stems from the fact that we can distribute this 1/n power to everything. So for so these two properties are actually related to each other. All right. So the quotient property, we can actually use the same thing, right? We can use the same property. Instead of multiplying, though, you're dividing. So you can split it up into a division problem with both radicals. So let's look at the product property first. So looking at this example, the cube root of 32, we can split this up into cube root of different numbers. So what we're going to do is we're going to break up 32 into a set of primes. So here we can break this up into 4 and 8. And then 4 can be broken up into 2 and 2. Circle your prime numbers. 8 can be broken up into 2 and 4. Circle the prime number there. And then 2 and 2. Circle those prime numbers. So now you're going to basically split this up into a bunch of 2's, right? So you could basically say that, well, this is just a cube root of 2 times the 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 cube root of 2. Basically saying that you have 5 of them, right? So this is what the property says that you can do. You can split it up into separate radicals. However, in the previous lesson, you may remember that what we did is we wanted to match the index to the exponent, right? So in this case, we're going to go ahead and collect these 3 2's, right? We're going to collect these 3 2's in order to become 2 to the 3rd power. And then in that way, you can basically cancel out the radical with the index, right? The radical with the power, and therefore you get the number 2. So basically, you pull that triple out and it becomes a 2. And then for this, well, you only have 2 of those. So we're going to go ahead and combine those and say that we have 2 to the second power. So we're just rewriting it. We're showing you how it looks like with all the 2's spread out. And now we're showing you with the 2's kind of combined together. Now in this case, the 2 and the 3 cannot cancel because they're not similar to each other, right? They're not equal to each other. So in this case, we have 2 from this guy, and then we just have the cube root of 2 squared. Now 2 squared is 2 times 2, which is going to be 4. Okay. All right, so this shouldn't be completely new because we kind of did this in the previous lesson already. But now, however, we haven't done quotients of radicals where you divide them. So you could, according to the property, you could split this up into the cube root of 32 divided by the cube root of 4. So that is perfectly allowed. So that is allowed for you to do that. However, sometimes it might be easier to just divide the numbers and then take the cube root. And then sometimes it's easier to do it this way. In this particular example, we have used the property, so we're done here. However, if I want to simplify this further, what I could do is I could divide the 2 numbers together, and I get cube root, well, 32 divided by 4 is 8, right? So we got the cube root of 8, and then the cube root of 8, well, 8 is 2 and 4, and then 2 and 2, so the cube root of 8, we have a triple here. So this is just cube root of 2 to the third, which this cancels, so this is basically equal to 2. All right, so basically all of this is saying that that's equal to 2. Those 2 are equal to each other based off of the property that we were talking about here. All right, so hopefully you have an idea of how to use the property. It's very straightforward. If you have a product, then you can split it into separate multiplications of radicals, or if you have a quotient, you can split it into 2 quotients separated by the fraction. Okay, so let's look at the example 2 here. We're going to actually be talking about products of radicals. So now we're going to be multiplying radicals together with the same index as well as with different indexes, or plural for indexes, indices. So we're going to look at the indices to see if it's the same or different first. So looking at the same indices case, according to the property, if we go back to the property here, you can only use this property when you have the same index. So you can only combine them into one number inside as long as the index is the same. You cannot do this for different indices. So what we can do is use the product property for the radicals. Since they have the same index, we can combine these under 1, like this. And we can multiply them inside. So 16 times 8. Okay, so then we got 16 times 8, which is, you can go ahead and multiply that out. In this case, you have the 5th root of 128. Okay, and technically you're done as far as multiplying. So you're done as far as using the property. However, if you want to simplify, so if you are simplifying here, then you're going to have to actually break apart the 128. So if you're going to do the 128, you do it like we normally do. We break it apart, so you can break it into 2 and 64, 2 and 32, 2 and 16, circle your primes, 2 and 8, 2 and 4, and then 2 and 2. So it looks like you have 7 2's. So this right here is 2 to the 7th power. However, you're looking for 5 of a number, right? So we're looking for 5 2's, like this. And then, so since we're looking for 5 2's, then I'll say I have 2 to the 5th. And then I have 2 2's left, right? So I'm going to go ahead and write that as 2 times 2, or 2 squared. And now these cancel, Or if you're like the method where you box the 5 2's, you can think of that as pulling out that 2. It's the same idea. And then you got a remainder of 2 2's. So 2 squared is 4, and then this is to the 5th root. So that's how it would look like if you're simplifying the solution. All right, so for the next example, notice that the, actually let's look at, let's look at the different index case. So since the indices are the same, we cannot combine them under one radical. So in order to do this, what we're going to do, the only easy way to do this is to convert these into rational exponents. So what do I mean by that? Well, converting them into fractional exponents. So we have here 8x, and then this is raised to the invisible 1 power. Remember that the template, the way to do this, to convert it, is power over index. So this is actually raised to the 1 over 6 power. Now we're going to go ahead and multiply by the other number, but we're going to convert this. This is raised to the invisible 1 power, and then the index is 3. So this is 2x raised to the 1/3 power. Again, you have to put the parentheses for this to be correct. All right, so now what we're going to do is we're going to go ahead and distribute the 1 over 6 to everything here. So we have here 8 to the 1 over 6 power, and then x to the 1 over 6 power. We're going to distribute that. Again, we're going to distribute the 1/3 to the 2 and the x here as well. Just like that. Okay, so now what we're going to do is we're going to combine these two x's together because they have the same base. So we're going to go ahead and add the exponents together now. We're going to add 1 over 6 with 1 over 3 because they have the same base. So these two x's combine. We have x to the 1 over 6 plus 1 over 3rd power. All right, now what about the 8 and the 2 here? So the 8 and the 2, you cannot combine them because they have a different base. However, what you could do is you can rewrite the 8 in terms of 2. This one's a little tricky to do, but imagine that if you break up 8 is the same thing as 2 times 4 and then 2 times 2. So 8 is the same thing as 2 times 2 times 2. So I can write this out as 2 to the 3rd power. So that's what I'm going to do. So I'm going to rewrite this 8 as 2 to the 3rd power raised to the 1/6 power because of the 1/6 there. Now remember, 2 to the 3rd power is 8, so this is equal to 8 right here. All right, now we got the 2 to the 1/3 power. I'm going to go ahead and bring that down. So the x's are done, except we need to add that. The 2's can be combined now. However, we're going to need to multiply these two exponents first. That's a power of a power property. So multiply those. So this is an invisible 3 over 1 here, an invisible 1. So 3 times 1 and then 6 times 1. So this is 2 to the 3/6 power. Which we're going to go ahead and reduce that now actually we're going to leave it as 3 over 6 power because we're just going to leave it as 3 over 6 power. And then x to the, now let's combine the 1/3 and the 1 over 6. So let's do that off to the side. The common denominator for these two is 6, so we need to times this by 2. So this is 1 over 6 plus 2 over 6 is equal to 3 over 6. And then we have here 2 to the 1/3 power. So now we're going to go ahead and combine these two. Now that they have the same base, we can combine it under one base. and then add the exponents together. And then we got x to the 3/6 power. Now you can kind of see why I left it as 3 over 6, because I'm going to have to combine these two fractions together. So I have 3 over 6 plus 1 over 3. If I left that as 1/2, I would have to convert it back to 3 over 6, right? Because the common denominator will be 6. So I'm going to times this by 2, times this by 2. I get 3 over 6 plus 2 over 6 is 5 over 6. So now I have 2 to the 5/6 power. And then I can convert this back to the 1/2 power. And I get something like this. So this is kind of simplified using the exponent properties. If I want, I can rewrite this. I can rewrite this in multiple ways. I can rewrite this as 2 to the 5/6 x to the 3/6 before I reduce it. And then I can convert that. Well, now I know that this is the 6th root. So I know that this is the 6th root of 2 to the 5th power and the 6th root of x to the 3rd power, again following the power over index rule. And so then I can combine these on the one radical, and I get 2 to the 5th x to the 3rd, or 32 x to the 3rd, 2 to the 5th being equal to 32. So I could write it like this as well. So this is an or. Again, a big or, because there's multiple ways that you can simplify. So either this or that, depending on if they're asking for the radical form or not. All right, go ahead and give it a try. Pause the video, try the problem. Okay, so this skill takes a little bit of practice. So if you don't get it at first, don't be discouraged. We're going to go through the solution together, and we'll see whatever steps you end up missing so that you can fix it. So here, there's an invisible index of 2 because it's a square root. And then here we got an index of 4. So clearly the indices do not match. So we're going to go ahead and write them out as, powers. So here we got 27x squared. So we got 27x squared raised to the, this is raised to the invisible 1 power right here. The whole thing, I mean. And then the index is 4. So I can raise this to the 1/4 power. And then this right here is raised again to the invisible 1 power. So I can multiply by 3x to the power over index, so to the 1/2 power. Okay, so now I'm going to distribute the these guys, these exponents, and I get 27 to the 1/4 power. X to the 2 times 1/4 is 2/4. And then we got 3 to the 1/2 power, and then x to the 1/2 power. Okay, so we can combine these two x's together. This can be reduced to x to the 1/2 power. So let's go ahead and reduce that to 1/2 power. And then so we can combine these and then add the exponents together. 1/2 plus 1/2. Now for this 3 and the 27, we cannot combine them. So we're going to try to convert 27 in terms of 3. So 27 is 3 times 9 and 3 times 3. So we got 3 to the 3rd power. So we might as well do that. So we got 3 to the 3rd power raised to the 1/4 power times this times bring down that 3 to the 1/2 power. So this is going to be equal to 1. So that's just going to be x to the 1 power. Let's combine these two 3's. Oh, let's multiply this together. So this is going to be 3 to the 3/4 times x times 3 to the 1/2 power. Now let's combine these two 3's together into 1 3 and add the exponents. So we got 3/4 plus 1/2 times x to the 1 power. Now we'll combine these. Now notice that the common denominator is 2, so this will be times 2 on top and bottom. So this will be 2/4, 3/4. So this will be 3 to the 3/4 plus 2/4 times x. 3/4 plus 2/4 is 5/4. So 3 to the 5/4 x. Okay, so we can leave it at this. Or if we want to simplify, this is saying that we got 5 3's and we desire 4 of them. So we're going to split this into the 4th root of 3 to the 4th and then the 4th root of 3 to the 1st power, knowing that we have 5 3's. But the reason I split it into 4 and 1 is to cancel these out. Don't forget the x there. And then now this cancels, so it leaves me with 3. Let's bring the x over to the front. And then we got the 4th root of 3. So either one of these suffice. This is more simplified technically, but this is fine, as the top one is fine as well. All right, so now we're going to talk about adding and subtracting radical expressions. So we talked about multiplying radical expressions. We talked about the division property. We're going to actually talk more about division after we do addition and subtraction, however. But if we want to add and subtract radicals, remember that adding and subtracting can be done to combine like terms, fractions with like denominators, and like radicals. So you can only add and subtract things that are alike in order to combine them. Like radicals have the same index and the same radicand. So they have to have both of those in order to become considered a like radical. Just like a like term has to have the same variables and the same powers, the radicals have to have the same index and the same radicand. In this case, x cubed and 3x squared are not considered like terms because they don't have the same power. In this example here, on the bottom, this has an index of 2 and this has an index of 2, and they have the same radicand, which is 20, so these are considered like radicals. So therefore you can combine them. Since they have the same index and everything, we can collect them together. So this is saying that we have 1 radical 20. This is saying that we got 3 radical 20s. If you combine them together, we can collect them and say we have 4 radical 20s. And that's what we're looking for. This is without simplifying, of course, because we can always simplify the 20 and break it down further. But we're not going to do that here. All right, now this second problem, these are not like terms. You don't have the same radicand, and you don't have the same index, invisible index of 2 here, and an index of 4 there. So therefore, we cannot combine this, and we're going to leave it as is. We cannot do anything else to this problem. So basically, this is the final answer if they were to ask you to simplify or anything like that. All right, so example 3. Let's look at another example. So if we want to combine, add, or subtract radicals, remember they have to be like. So right now, we can see that these are like radicals because they have the same index. However, they do not have the same radicand. So technically, they're not like radicals because of that purpose. So basically, they're half alike. So in order to make them fully compatible, we have to make these radicands the same. Same thing for the first and the last one. They have the same index, but they don't have the same radicand. So what we're going to do is we're going to make the radicands the same by splitting this 20 and by splitting the 250 and the 16. Notice that the 5 cannot be split, so we're going to leave that one alone. So 20 is 2 times 10, and then 10 is 2 times 5. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. 250 is 5 times 50. 5 is 5 times 10. 10 is 5 times 2. Okay, so now we're going to simplify this. Since we got a pair of 2's, we're looking for pairs here. We can pull that pair of 2's out, and so we end up having a 2 and then a 5 left over on the inside. Here we're looking for cubes, so we're looking for a perfect cube. So we got 3 2's there. We're going to pull that those 3 2's out. And then we got a leftover 2 inside the radical. Here we're looking for triples as well. So we got a triple 5. So we can pull that out as 1 5. And then we got a cube root of whatever's remainder is 2. And then here we just have minus square root of 5. So now you can tell that these are now considered like radicals because they have the same radicand and the same index. Similarly, these two cube roots are alike because they have the same index and the same radicand. So we can go ahead and combine those like terms. So we're going to go ahead and combine the 2 radical 5 minus 1 radical 5. So we got 2 radical 5, 2 square root of 5 minus 1 square root of 5. We can combine those. And 2 minus 1 is 1. So we're left with 1 radical 5. Of course, we don't have to write the 1 there, so I'm going to go ahead and erase that. Now we can combine these two together. We have a negative 2 radical 2 plus a 5 radical 2. So negative 2 plus 5 is 3, a positive 3. So we're going to say this is positive 3 cube root of 2. And there's my answer. I cannot combine that any further because those are not like radicals. Pause the video and try the following problems. All right, so let's look at the first one here. Notice that we have 2 cube roots, so we're going to probably consider combining those as long as these radicands are the same. So we're going to go ahead and break them down as much as we can. So I know that this can break down, we can break this down multiple ways, but let's go ahead and break it down like this. Let's do 20 and 10 and 20 and 100 because we got 3 zeros there. And then 20 is 5 and 4. Circle that 5 because that's a prime. We got 2 and 2 there, so that's done. 100 is 2 and 25. And then 25 is 5 and 5. Okay, we can break down the 2 here. We can break down the 128, 2 and 64, 2 and 32, 2 and 16, 2 and 8, 2 and 4, and 2 and 2. All right. So here we're looking for cubes, and so we're looking for 3 of a number. So looky here, we have 3 5s and we got 3 2s. So this actually works out very well. So this is actually a perfect cube, surprisingly. Let's see here. 5 4. I want to make sure that this is right. This is not right because I messed up the number here. I apologize. 100 is not 2 and 25. 100 is 2 and 50. So we're missing some numbers here. And then 50 is 2 and 25, and then 25 is 5 and 5. Hopefully you guys caught that before I did. So yeah, that is the correct multiplication, or the correct factorization. So now let's go ahead and do the triples. So we still got the triple 5s, of course, so that works out. We got a triple 2s still, but then we got a leftover 2 here, so that stays inside. Okay, so we got a, so the 5 goes out and the 2 goes out, which means we got a 5 and a 2 on the outside, so we got to multiply those. We got a cube root, we got a 2 left over on the inside. We can't do anything with this, so leave that alone. This one, we have a triple set of 2s and another triple set of 2s, so we can pull those out on the outside, so that'd be two 2's on the outside, 2 times 2, and then this 2 is left over on the inside. So we got 5 times 2 is 10, so we got 10 times cube root of 2 plus square root of 2, and then we got 2 times 2, that's 4, so 4 times cube root of 2. The only ones that are considered like terms now are the cube root of 2 and the cube root of 2, since they're the exact same. We have 10 cube roots of 2 for this one, and we have 4 cube roots of 2 there. So we can combine them and say we have 14 cube roots of 2. And then we're going to add that to the square root of 2 here. But we can't combine those because they're not like terms. All right, so looking at the second problem, we have 3 of the same index, but unfortunately they're not the same radical. However, we're going to radicand, so therefore we're going to try to split them as much as we can to see if we can find any like ones. So 20 is 5 and 4. 4 is 2 and 2. 600. 600 is 10 and 60. 10 is 5 and 2. 60 is 5 and 12. 12 is 3 and 4. 4 is 2 and 2. 125 is 5 and 25. 25 is 5 and 5. So now here we're looking for pairs, right? So we got a pair of 2's here. Pull that out. So this will be a 2 on the outside and a 5 left over on the inside. Minus, we got a pair of 5's here. We got a pair of 2's here. And we got a 2 and a 3 left over. So we got to multiply those back in. So we got a 5 that we pulled out and a 2 that we boxed that we pulled out. So we got a 5 and a 2 outside. The rest that is inside is the 2 and the 3. So that's 2 times 3. I'm going to go ahead and bring this down so we have enough space. Okay, so now here we have a pair of 5, so we can pull that out. So we got minus, so that 5 goes out, this 5 stays in. All right, so let's simplify this a little bit. This will be 10, and then that'll be a 6. So we got 2 radical 5 minus 10 radical 6 minus 5 radical 5. So we have these two radicals are the same because they have the same radicands. So we got 2 square roots of 5 minus 5 square roots of 5. So 2 minus 5 is negative 3. So we can combine these two and we get negative 3 radicals of 5 and then bring this down, minus 10 radicals of 6. All right, so now we're going to consider multiplying radicals that are binomials, right? Or multiplying a monomial with a binomial radical expression. So this right here is considered a binomial radical expression right here. So this is a binomial radical expression. And these are 2 binomial radical expressions. Remember, a binomial is 2 terms and a monomial is 1 term. So in order to multiply with binomial radical expressions, you're simply going to follow the same rules of multiplication and the multiplication properties of radicals. So you're going to be distributing this guy just like you normally do with numbers. So now we have the cube root of 7 times 2. If you want to multiply a whole number with a radical, you simply have to put the number and the radical together like this. Okay, so this will be 2 cube root of 7. That's how you multiply those 2 numbers together. You cannot multiply the 2 inside because the 2 doesn't have a radical. All right, so now we got cube root of 7 minus cube root of 49. Since they have the same index, we can use that radical property and multiply those together. So we have minus cube root of 7 times 49. Okay, and I forgot the cube root here. All right, so now what we're going to do is we're going to simplify this a little bit. So we're going to actually, what I'm going to do here is I'm going to actually leave this as 7 times 49 because I know that we have 7 and 49, And then we can break it up further into 7 and 7. 7 times 7 being 49. And that means that we got a triple of 7s, which is what we want here, right? So I'm going to go ahead and save me some time and just go ahead and box that 777 that I know I have, and I can pull that out. So the cube root of this here is just going to be 7 because this pulls out as a 7. So this will be minus 7. This saves me a whole bunch of time here. So we got 2 times the cube root of 7 minus 7. And I can't combine those anymore because they're not like radicals. So this one just required a little bit more simplifying with that little trick. Part B, you have now a binomial with a binomial, which means you have to use the good old FOIL. First, outer, inner, last. So we're going to do the first terms first. 2x times 2x is 4x squared. So that's first. Next, we're going to do the outer terms. So we got 2x times negative square root of 3 is negative 2 square root of 3 x. Notice that the x is on the outside, not on the inside of the radical. We simply put the two numbers together and then we have x next to it. That's all we do when we multiply those. Since they're not like terms, you just put them next to each other like that. Next, we're going to look at the inner terms. So we got to do 2x times square root of 3. So you just put them next to each other since they're not compatible. So we're going to do 2 times the square root of 3 and then x on the outside. Leave it like that. Lastly, we're going to do the last terms. We got square root of 3, positive square root of 3 times negative square root of 3. So we can multiply those together because they have the same index, right? So we're going to do, and we have a positive and a negative, which is a negative. And we're going to multiply those inside the radical. So we got to do 3 times 3 on the inside, which we know 3 times 3 is 9. So let's just go ahead and change this to a 9. All right, so now we have these two are considered like terms because we have the x's and we have the same radicals, all that stuff. So we can combine them. A 2 radical 3 and a negative 2 radical 3 cancels out. Next, we're left with 4x squared minus the square root of 9. But we know that the square root of 9 is 3, so we can change this to a 3. So we have here 4x squared minus 3 as our final result. Pause the video and try the following two problems. Alright, let's look at the first problem here. Just like before, we're going to distribute. So we got square root of 6 times 5. Since they're incompatible, they're not like terms, you're going to put them together. 5 times the square root of 6. Now we got the square root of 6 times the square root of 3. These are compatible. They have the same index, so we can multiply them under the same radical. So we can do radical and then 6 times 3. So we have 5 square root of 6 plus the square root of 18. Next, we're going to split this radical because we want to simplify this a little bit more. So we can split this up into 2 and 9, and then 9 into 3 and 3. Since we're looking for pairs here, we box the pair goes out, the rest goes in. So we got 5 square root of 6 plus that 3 goes out, we got a radical 2 there. Now notice I can't do anything with the 6 because 6 is 2 times 3 and I have no pairs. So therefore I'm going to leave that one alone. Also, I can't combine the square root of 6 with the square root of 2 because they're not like radicals because they don't have the same number inside the radical sign. So I'm done here. Alright, so here we're going to be doing the good old FOIL. So we have the first set of terms. X times x is x squared. Next we have the outside terms. X times square root of 10 is square root of 10x. And that's positive because we got a positive times a positive. Next we have the inner terms. So we have positive square root of 10 times positive square root of x, again being the same thing that we got earlier. And then lastly we have the last terms. Square root of 10 times square root of 10, both positive, give you a positive number. So we got to do square root of 10 times 10 because they're the same radical. We can multiply inside. So this is going to be 100 right now, so I'm going to change that over to 100. These are like terms, so I can combine them. So I have 1 square root of 10 and then another square root of 10. 1 square root of 10 plus 1 square root of 10 is 2 square root of 10. So this becomes 2 square root of 10x. Keep in mind that this square root of 100 is 10, and then this is going to be x squared, and then this is positive. Notice we can't combine any other like terms because that's an x and that's an x squared. Everything is just not right. So as far as nothing is alike. So we're going to leave it like this. All right, so now we're going to look at the quotient of a radical and rationalizing the denominator. So in order to divide radicals, and we're going to need to know the skill of rationalizing. Rationalizing the denominator, what that means is you're going to get rid of any radicals in the denominator so that the denominator has only rational numbers. So no radicals, only whole numbers, right? Only rational numbers or numbers that can be written as fractions, okay? So we're going to look at two cases here, one with a monomial denominator, one with a binomial denominator. So for the monomial denominator, I'll give you a couple examples here. Notice that the index here is an invisible 2, so I'm going to use the quotient property that I mentioned earlier and split this up into two radicals like this. And I don't have to write the 2 there anymore. So we have the square root of 2n and then the square root of 9m. You may recall that this is one of the properties that you can split the radical in the top and the bottom. So now what we want to do is we want to get rid of the radical on the bottom. So we want to rationalize. In order to do this, we're going to have to multiply by, we're going to have to get rid of that square root. The only way to get rid of that square root is to multiply by the same thing on the bottom. The reason why we multiply by the same thing is because 9m times 9m is 9m squared. And a square and a square root will cancel, therefore getting rid of my radical. Now, if I do the same thing, if I do something on the bottom, I have to do the same thing on the top. So I'm going to simply multiply the same thing on top. Now, we're going to go ahead and multiply. Now we can multiply inside the radical. So we have a square root of 2 times 9, 2n times 9m. So 2n times 9m is 18mn, just put it together. And then the square root of 9m times square root of 9m, well, that's the square root of 9m squared, right? Because we have 2 of them. Now, because we have a squared and a square root, they cancel, which is the whole point of rationalizing, is to get rid of that radical. So now we have the square root of 18mn over 9m. All right, so now what we're going to do is we're going to simplify this a little bit. Actually, yeah, now that we think of it, we could split up the 18, right? So the 18 could split into 2 and 9. 9 is 3 and 3. We can box that pair of 3's. That 3 goes out, so we have a 3 on the outside. And we have a 2 on the inside left over, so we have 2mn over 9m. And then we can, you see this fraction here, 3 over 9? We can reduce that. So let's reduce that by dividing by 3, so it just looks simpler. And we get 3 divided by 3 is 1, so we got square root of 2mn over 3m. Now notice notice that this became an invisible 1, which I'm not going to write, okay? So this is the fully simplified version. All right, now let's look at the rationalization for the second problem here. Now this problem has a cube root. So we're going to split this in terms of the cube root instead of the square root. Now, we want to get rid of this cube root. This is not the exact same problem because it's cube root instead of square root. How do I get rid of something if it's a cube root? Well, notice that I only got not one 9m here. I got 9m to the first power. So the only way to cancel out the cube root is if I have 9m to the third power. So the only way I can get 9m to the third power is if I multiply by 9m squared, right? So in order to get rid of this radical, I need to multiply by the cube root of 9m squared. Therefore, now this will give me 1 and 2, which is a total of 3. So now this is officially, done as far as like the rationalization. Now we had to actually do the same thing on the top, of course, but we actually figured this out together. That's how you would do it. Now, if this were a 4 instead of a 3, then you would have to multiply by the fourth root of 9m to the third power, because then you have 3 and 1 is a total of 4. All right, so the point is to get the power to match with the index. So now we're going to go ahead and multiply this together. On the bottom, we get the cube root of 9m to the third because of the 1 and the 2. On the top part, we have the cube root of 2n, and then we're going to multiply that with 9m squared. So 9m squared, well, 9 times 9 is 81, and then m squared is, or m raised to the second is just m squared. So again, don't forget to distribute that. So we have here cube root of 2n times the cube root of 81m squared. And then since these have the same index, we can multiply them under the same radical. So we can do 2 times 81. So we get the cube root of 2 times 81 is 162. And then we got m squared n all over. Now this cube and this cube root cancel, which is the whole point of doing this, right? Over 9m. Now, you may be asking yourself, can I break down 162 further? The answer will be no, technically. Actually, now that I think of it, 9 times 9 is 81. You can actually break it apart if you did it, like if you did all of it, you can find 3 of a number actually, because we got a 2 and an 81. So let's actually do that off to the side. Initially I thought there won't be 3 of a number here, but there actually will be 3 of a number. We got 2 times 81, and then 81 is 9 times 9, but then 9 is 3 times 3. So actually there will be 3 of a number. So we can actually simplify this. Let's pull the 3 out there. So if we pull that out, that pulls out because we're looking for triples here, that's why. So we could pull that out, and then we're left with a 2 and a 3 left over on the inside. So we have here the 3 on the outside, we have the cube root, we have the 2 and the 3 left over on the inside. So let's go ahead and multiply that. 2 times 3 is 6. So 6m squared n over 9m. I'm going to go ahead and reduce this 3 over 9, divide by 3, top and bottom. And we get the square root of 6m squared n. 3 divided by 3 is 1, so I'm just going to ignore that. 9 divided by 3 is 3, so we get 3m. I forgot the cube root there. There you go. All right, so a lot that goes into rationalizing. However, this is simpler than it was before because, one, we reduced the radicand, but we also got rid of the radical in the denominator, which makes it simpler. All right, so now we're going to talk about how to rationalize when you have a denominator that's a binomial. How do we go about doing this process? Well, if I want to get rid of the radical, I can't just multiply by the same thing. The reason why I can't multiply by the same thing, so you may think, well, what if I multiply by 2 plus square root of 5? Or what if I multiply by the square root of 5? That won't actually work, because if you multiply by 2 plus square root of 5, you're going to end up having to FOIL that. And when you FOIL it, it just won't work out. You could try it and FOIL it, and you'll see that you won't end up getting rid of the square root. Same thing with the square root of 5. You're going to have to distribute that to both of them, and that's not going to get rid of it. So what's our solution? Our solution is to not multiply by the 2 plus square root of 5, but instead multiply by 2 minus the square root of 5. In other words, we multiply by the conjugate. So there's our word there, conjugate. We mentioned that word before earlier in the first half of the year. But the conjugate is the same expression, but with the opposite sign in the middle, essentially. So we multiply by, in this case, 2 and square root of 5. So the same numbers, but the sign in the middle is the opposite sign. So this right here is the conjugate of this. Okay, so those are they're conjugates. If I do this on top, I have to do it on the bottom as well. All right, now if I look at the other one, just real quick, I have a binomial denominator, so I'm going to multiply by the conjugate of this guy. So which means I gotta switch that sign. So I'm going to multiply the bottom by the square root of 5 plus the square root of 3. So in the case the conjugate is the positive version on the middle, and then whatever I do on the bottom, I do on the top. So that's how you do that step. Multiply by the conjugate. Now, next we got to actually do the math, of course. So we're going to have to FOIL the bottom, and then we're going to have to distribute on the top. Fortunately, that's just a 1, so it doesn't really do anything. 1 times 2 is 2. 1 times square root of 5 is square root of 5. So on the top, we have 2 minus square root of 5. On the bottom, though, we are going to have to do a FOIL. So we got first, so we got to do 2 times 2, which is 4. Outer, 2 times negative square root of 5 is negative 2 square root of 5. Inner, 2 times square root of 5 is positive 2 square root of 5. And last, square root of 5 times negative square root of 5. Square root of 5 times negative square root of 5 is negative square root of 5 times 5, which is 25. All right, so we know that the square root of 25 is 5. What about the middle? Well, we got negative 2 square root of 5 and then a positive 2 square root of 5. So those cancel. And we know that this is going to become a 5. So we got here 4 minus 5. So we got 2 minus square root of 5 over 4 minus 5. 4 minus 5 is negative 1. So we got 2 minus square root of 5 over negative 1. We got rid of the radical. So there's no more radical in the bottom, which is great. So now we're going to go ahead and, do you see this negative here? We're going to distribute the negative. So we're going to divide everything by negative 1. So 2 divided by negative 1 is negative 2. Negative square root of 5 divided by negative 1 is positive square root of 5. So basically dividing by that negative just kind of flips the signs. And that's our final answer. All right. So let's go ahead and look at foiling this part. This part is going to be more extensive because we have to FOIL the top and the bottom. So let's go ahead and FOIL the top. So we got 5 times 5, or 5 times the square root of 5, which is 5 square root of 5. We got 5 times positive square root of 3, which is 5 square root of 3. We have negative 2 square root of 5, or negative square root of 2 times square root of 5 is negative square root of 2 times 5, which is 10. we have negative square root of 2 times positive square root of 3, which is negative square root of 2 times 3, which is negative square root of 6. And then on the bottom, we have square root of 5 times square root of 5 is square root of 25, positive. Square root of 5 times square root of 3 is positive square root of 15. Negative square root of 3 times square root of 5 is negative square root of 15. Negative square root of 3 times positive square root of 3 is negative square root of 9. Alright, so square root of 15 and square root of 15 here cancel, so which is good. That's what we wanted, right? So that cancels. Square root of 25 is 5. Square root of 9 is 3. So we have on the bottom 5 minus 3. And then of course we have all these radicals on the top, so I'm just going to rewrite them. And 5 minus 3 is 2. Over 2. So we got rid of the denominator, the radical in the denominator, so it looks simpler in a way. So now we're going to distribute the 2 to everything here. So we're going to do 5 divided by 2, 5 divided by 2, and then there's an invisible 1 here divided by 2, and there's an invisible 1 here divided by 2. So I'm just going to write this as 5 halves square root of 5 plus 5 halves square root of 3 minus 1 half square root of 10 minus 1 half square root of 6. Okay? So you don't have to write it like that. It's just another way of writing it. So you can write it like this, or you can write it like this. They both mean the same thing. We can't combine any of the radicals because they're all different. We have a 5, a 3, a 10, and a 6. All right, pause the video and try the following problems. All right, this is the last stretch here. Dividing by simplifying and rationalizing the denominator. Last skill here. There's a lot of stuff going on in this lesson with radicals, all the operations. All right, so let's look at the this problem here. We're going to split this up into the radical 5, top and bottom. All right, so now we have them split, we need to rationalize. So since I got a monomial here, I'm just going to multiply by whatever gets me to match to this 5. Right now, this is a 16x to the third raised to the invisible 1 power. So I need 4 more of these guys in order to make this to the 5th power, right? So what I'm going to do is I'm going to multiply by 4 of them. So I'm going to multiply by the 5th root of 4 of these guys. So 16x to the third raised to the 4th power. And therefore 4 and 1 will give me 5, which will match up with the index of 5. Whatever I do on the bottom, I do on the top. All right, so now we have on the bottom, here I need to give myself some space here. So on the bottom we have the 5th root of 16x to the third raised to the 5th power, because 1 and 4 is 5. And then now we got 5 and 5, they cancel, which is the whole point of this. And now for these guys, we're going to go ahead and let's see here. This is a big number, 16 to the 4th power. So I'm just going to write it as 16 to the 4th power, but I'm not going to multiply it out just yet. And then I'm going to distribute the 4 to the 3 here, so that would be 12. So I get the 5th root of 7 times the 5th root of 16 to the 4th, and then x to the 3 times 4 is 12. All right, so far so good. So on the bottom we just have 16x to the 3rd power, because the radicals in the 5 canceled. And we're going to multiply these two together. So we got the 5th root of 7 times 16 to the 4th times x squared. Now we need to just make this look simpler, make this look nicer. So notice that we have, instead of multiplying all this number, is because I know that is going to be a very big number, what I'm going to do instead is I'm going to leave it as 7 times 16 to the 4th power. So this means I got 7, 16, I got 16, 16, and 16. So I got 7 and 4 16s. So let's break this up further. This is a prime number, right? So what I can do is that's 16 is 2 times 8, 2 times 4, and then 2 times 2, right? So basically 16 is equivalent to 4 2s. And this is going to be equivalent to another 4 2s. This is going to be equivalent to another 4 2s. And this is going to be equivalent to another 4 2s. So we have here a total of 4, 4, 4, 4. That's 16 2s. So we have 16 2s here. That's a lot of 2s. So I'm going to take this, I'm going to replace it with another 2 to the 4th. Now, 4 2s, 4 2s, 4 2s, 4 2s, and then a 7. A big number indeed. This is a very large number. But remember that we're looking for 5th. We're looking for 5 of them, right? So if we have 16 2s, how many, so let's say we have 16 of these. How many of these can we split into 5s? Well, how many 5s can fit in 16? Well, that would be 3 5s, right? 5 times 3 is 15. So I could take these 16 2s and I can split it into 2 to the 5th power, 2 to the 5th power, 2 to the 5th power. So that's a total of 15, right? And then 2 to the 1 power. Hopefully you were able to follow up with that logic. So like 4 or 16 2s is the same thing as 15 2s and then 1 2, because 5, 5, and 5 is 15. Okay, why do I do it that way? Well, because I have a 5th root. So I can now simplify this and say, well, this is the 5th root of 7. I'm gonna leave the x alone for now. I'm gonna get to the x later. The 2 to the 5th power, the 2 to the 5th power, the 2 to the 5th power. I'm talking about these three ones here, and then another. There's a 5th root there, and then a 5th root of 2 to the 1 power. This guy here. Now these cancel out. If you look at it, cancel, 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 cancel. So we got 2 times 2 times 2. 2 times 2 times 2 is 8. So this is going to be 8. So I'm going to just bring that over to the side here. 8 times the 5th root of 7. 7 and then x to the 12th, and then I got 5th root of 2. All right, so now I got 12 x's. How many 5s can fit in there? Well, that would be 2 5s, right? So I can write this as x to the 5th, and x squared. 5, 5 is 10, 10 and 2 is 12. I write this out as 5th power, or 5th root, 5th root, 5th root. These cancel, so it leaves me with x squared, and then 5th root of x squared. Now this is, more advanced and more convoluted, so you just have to be careful with your calculations here. So now we have x squared, so we have 8x squared. Let's put those together. We got the 5th root of x squared. We got the 5th root of 7. We have the 5th root of x squared. And then, of course, we have the 5th root of 2 here. Let's combine these under one radical, just to make things simpler. The 5th root of 7 times 2 is 14, x squared. All right. That was only difficult because it was such a large number. If we were to multiply this number right here, if we were to multiply 16 to the 4th times 7 right here, 16 to the 4th alone is a huge number. Let's show you what that number is. That number is 65,536. And then we had to times that by 7. That would have given us a huge number. So what we did here is cut down on the calculations by just breaking it down right away. Even so, it was still a tough problem. So this is our final answer. this is it for the video, guys. There was a lot going on in this lesson because we covered the for operations, we covered rationalizing, and we covered simplifying. So there's a lot going on. I hope you learned something from this lesson, and I'll see you in the next video.